Welcome back. We continue in this lecture with the basis of approximations. We learn how to make and justify approximations in engineering sciences. We, in the last lecture, had analyzed the problem of damped oscillators starting from the governing equations and the initial and boundary conditions. We showed that the two non-dimensional pi numbers CTC by m and KTC square by m measured the relative magnitudes of the damping force and the spring force terms respectively. Here Tc stands for a characteristic time. We could arrive at these estimates of relative magnitudes directly from the scale factors as well without invoking the governing equations, and that's what we will do now. In this example, there are three forces: the inertial forces, damping forces, and the spring forces. We write the law for each force. The inertial force is Ma, damping force is Cv, where C is the coefficient of damping, and spring force is Kx, where K is the spring constant. We can convert these laws into scale factors relations like here. And then by equating the scale factors of these two forces, we can get this as a pi number. And by equating inertial and spring forces, we could get this as the pi numbers. The first pi number CTC by m is the ratio of the damping force to the inertial force, while this last one is the ratio of the spring force to the inertial force. We could similarly obtain the relative magnitudes of the terms in baked potato problem using the scale factors for the energy currents. The three energy currents are important: conduction in solid, convection, and heat storage in solids. The applicable relations: Q dot is area times the conductive heat flux. So it is area times Ks d theta by dx. And so the scale factor relation is the scale factor for conduction in solids, Kcs, is the scale factor for the conductivity of solids, Ks times Kl times K delta theta. From this, we obtain this as the primary pi number, Q dot Cs divided by Ks L delta theta, where the characteristic nature of the quantities involved is understood. Similarly, the applicable relation for convective flux or the convective current is Q dot is equal to A times the convective flux given by the Newton's law of cooling. So this is AH delta theta, and so K of the convective flux is Kh times Kl square K delta theta. The heat storage in solid is the mass rho V the volume, Cv the specific heat, and delta theta by delta T. And from this we get the scale factor relation as Ku is equal to K rho, Kl cubed, Kcv, K delta theta divided by Kt. And so this is the resulting pi number. From the first two, we get pi number as the pi number, and this HL by Ks now can be seen as the ratio of the convective flux divided by the conductive flux in solid. And from the first and third basic pi numbers, we get L square rho Cv divided by Ks tau. Ks divided by rho Cv is replaced by alpha, the thermal diffusivity of the solid material, so that we get L square by alpha tau as the Fourier number. And this is the ratio of his storage in solid divided by the convective flux at the boundary. So thus we see in both these examples, we obtain the same ratios of the forces or the same ratios of the fluxes as we obtained from the original governing equations and boundary conditions. There is no need to start from those equations. We could start from this considerations of scale factors relation. Let's do a new example, the spreading of oil slick on oceans. When an oil is dumped in an ocean, the oil spreads out on the seawater. This spreading of oil on seawater is controlled primarily by the viscous forces that the seawater applies on the slick, the unsteady inertial forces in the oil, the buoyant weight of the slick, that is its own weight minus the buoyancy, and the surface tension forces. It is asserted that the surface tension forces are insignificant to begin with and come into play only after the slick is very thin, which may be days after the slick. How long before the surface tension forces come into play? We have to determine this. So we'll take the law approach. Since we are worried about the surface tension forces and when they come into play, let's begin with estimating the surface tension forces and then compare it with one of the other forces, say the inertial forces. The surface tension forces are estimated as F sigma c, which is approximately sigma times Lc, where sigma is the surface tension between the spilled oil and the seawater. This red drop represents a mass of oil on seawater. The surface tensions acting on this with the angle of contact act in these directions, and the component of these horizontally will try to oppose the expansion of the slick. The unsteady inertial forces on the slick are estimated as mass times the acceleration dv by dt. So that is like rho Lc cubed times Vc by Tc, or rho s Lc cubed Vc divided by Tc, where rho s is the density of the slick. The surface tension forces are negligible as long as F sigma c divided by Fic, which is rho Tc divided by rho s Lc square Vc is small compared to unity. That is, this is the ratio. As long as this is less than 1, the surface tension forces are small compared to the inertial forces. The characteristic length Lc of the slick can be taken as the cube root of the volume of the oil that has been spilt on the ocean. The velocity Vc can be estimated as LC divided by TC. And so the actual time T can be used for TC, and then the relevant criteria for neglecting the surface tension forces is that sigma T square divided by rho S V be less than 1, or T be less than under root rho S, the volume V divided by sigma, the surface tension. So surface tension does not come into play for times less than under the root rho S volume divided by surface tension. The typical values of rho S and V, this may yield a period of several days during which surface tension forces are not significant. One estimate of a seawire and crude surface tension force is sigma is equal to 0.02 Newton per meter. 100,000-ton oil spill is considered a medium size spill. For this spill, the above equation suggests the surface tension forces do not show up for times of the order of 23 days. It is only after 23 days would the surface tension force would need to be considered. This picture shows an oil slick in the Gulf of Mexico that has been spreading since 2004. You see the rainbow colors. The colors are visible only for film thicknesses between 150 nanometers and 1 micrometer. So this suggests that in the last 18 years, the film has spread so much that its thickness is now of the order of 1 micrometer or less. Let's do another example, an interesting example of flow past a pulsating sphere. Consider the flow of a uniform stream of fluid at a velocity v0 about a pulsating sphere whose diameter can be represented as d0 into 1 plus epsilon sine omega t, where epsilon is small. Under what conditions can the flow be treated as quasi-steady flow? What would a quasi-steady flow mean in this context? A quasi-steady flow would mean that at any given instant, the flow would behave like a steady flow. That is, we could neglect the inertia forces. But the flow is not really steady. It is changing with time. Because at any given time, it must accommodate the boundary conditions. That is, the normal flow at the surface of the sphere is equal to the velocity of the surface, or the diameter is as it is. The unsteadiness in the flow enters through the normal velocity boundary condition that the normal velocity of the fluid at the surface must be equal to the normal velocity of the surface itself at every instant of time. Since the diameter of the sphere varies like d is equal to d0 into 1 plus epsilon sine omega t, the normal velocity of the surface is the first derivative of d, which gives 1/2 epsilon omega d0 cosine omega t. And the acceleration on the surface is like another derivative of this, and this would be like epsilon omega square d0 sine omega t. So we know what is the acceleration at the surface. And if we know this, we can estimate the unsteady force, the unsteady inertia in the fluid. The scale factor for that, Kfu, is K of mass times K of acceleration, which is epsilon omega square d naught sine omega t. So Kfu is K rho KL cube, which is K for mass, and this is the K of acceleration from here. This gives the unsteady force varies like epsilon rho omega square d naught raised to power 4. This is the unsteady force. If Fi is the force of convective inertia in the force, then Kfi is K rho KL square Kv square. This we have obtained a number of times earlier. So this gives you Fi is like rho d naught square V naught square. So the unsteady force is this, and the inertia force of convective acceleration is this. So the unsteady force can be neglected if epsilon rho omega square d naught raised to power 4 is much less than rho d naught square V naught square, which gives epsilon omega square d naught square by V naught square is much less than 1. That is, the unsteady forces can be neglected if epsilon times the Strouhal number squared is much less than 1, where the Strouhal number is omega d naught divided by V naught. If this condition is obtained, then the flow can be taken as a quasi-steady flow about a sphere having the instantaneous value of the diameter. Another example, the decay of a vortex. When an aircraft takes off from a runway, a swirling flow is set up. This picture, which is from original flow visualization experiments of Ludwig Prandtl from the turn of the last century, shows an aerofoil moving in that direction, and when the aerofoil moves in that direction, there is a vortex that is formed in the flow. And as the aerofoil moves away to the left, this vortex stays there. In an actual aircraft, this vortex, which is termed as a starting vortex, is formed at the airport. And as the aircraft takes off, this vortex is left on the runway and decays with time. This swirling flow, as I said, is termed as a starting vortex, and the flow within it is modeled by a free vortex in which the velocity components are given by V theta is equal to K by R and VR is equal to 0. No radial velocity, and the tangential velocity varies inversely with radius. Small, far away, and increasing as you move towards the center of the vortex. This is the kind of the tangential velocity profile that we get. As R decreases, the velocity increases. The large velocity gradients near the origin set up significant viscous forces, changing the flow pattern with time. We show a similar flow. Here, a flow in a tornado is a swirling flow that goes around like this. The velocity is large at the center and small far away at any given cross section. These large velocities near the center give rise to very low pressure that picks up the debris from the ground, and so that makes the core visible. The core is also visible because of condensed moisture in there at low pressures. This velocity profile V theta versus R, because of the large gradient near this, the flow near the center is viscous, and since it is viscous, it's more like a forced vortex where the velocity varies directly with R, increases with R. And after achieving a maxima, the free vortex takes over and the flow velocity varies like this. The viscous action in this core results in dissipation of energy, and the time the velocity profile changes. The location of the maximum velocity marks the edge of what we can consider as a core. So as time increases, the radius of the core increases. The region where viscous forces are predominant and the velocity differs significantly from the free vortex field is termed as the core of the vortex. This graph shows the actual radius versus velocity of an actual tornado, which is known as a Spencer tornado in literature, and a predicted model by Howe, which has been published recently. And this is based on considering a viscous course superimposed on a free vortex. We have to deduce how the radius of this core varies with time. So we obtain the estimates of the various forces. The viscous forces and the unsteady forces are the two relevant forces in this decay. The viscous forces can be estimated, as always, as F mu is equal to mu Vc Lc, exactly the same as we obtained a number of times earlier wherever we estimated the viscous forces. And the unsteady forces are like mass times the acceleration. The unsteady acceleration with time, and that is Vc divided by Tc. And so the viscous forces are negligible whenever F mu is much less than Fu, which gives us that the characteristic length is like under root nu Tc. If we take the characteristic time at the actual time, then the radius of the core would be like the characteristic length, and that varies like under root nu T as a square root of time. Another example, let's calculate the time required to acquire the terminal velocity in a low Reynolds number flow. When a ball falls in water or a helium balloon rises in air, a steady velocity, termed as the terminal velocity, is attained when the drag force on the ball or the balloon becomes equal to the net weight. For what order of time the accelerating motion cannot be neglected? This is of the same order as the time required to acquire the terminal velocity. Also determine the time after which the unsteady inertial terms for the fluids are important too. The earlier case was when the unsteady forces of the solid were important. Now we ask the time after which the unsteady inertial forces for the fluids are also unimportant. Then as a numerical we will do for a steel sphere of diameter 0.1 millimeter, a very tiny steel sphere settling in water, we estimate these two characteristic times and then try to explain the physical significance of these two times. There are 5 kinds of forces in this problem. The inertial force of the sphere itself, the mass of the sphere times the acceleration of the sphere. Unsteady forces. For sphere, there will be only unsteady forces. There is no convective acceleration for a solid sphere. The gravity forces of the sphere are the net of the weight and the buoyancy, and they would be like the density differences of the solid and the fluid, the volume and the acceleration due to gravity. Viscous forces, as before, would be like mu Vc d. C everywhere stands for the characteristic value of the relevant quantity. The inertial force of fluid convection, and that also we obtained many times as rho f times d square Vc square, which is exactly the mass rho f d cubed times the convective acceleration, which is like v dv by dx. V dv by dx would be like v square by d. So the net is this rho f d square v square. And the unsteady fluid inertia from the mass of fluid times the acceleration, which is Vc Tc. We take two forces, this and this, and from this we construct ratio of the inertial force of the sphere to the viscous force as rho s d square divided by mu Tc. Thus, the unsteady forces on the solid can be neglected if rho s d square mu divided by mu t is less than 1, or for times greater than rho s d square mu. For a steel sphere of diameter 0.1 millimeter settling in water, the density of steel is 7.480 into 10 to the power 3 kilogram per meter cube. And so this time is obtained at 0.028 seconds, a very small time. less than 300ths of a second, after which that steel sphere would have acquired a constant velocity, the terminal velocity. This is because of a very low diameter of the sphere, which results in a very small Reynolds number. Now let's look at when the unsteady inertial forces in the liquid can be neglected. Following the same logic, the unsteady or inertial effects in liquids are negligible for T less than rho f d square divided by mu. From this and this. So we get T greater than mu f d square by mu. We can neglect the inertial effects of the fluids. This time for a sphere of diameter 1 millimeter is 0.011 second for water. Rho f, we have to choose the fluid. So we choose this as water, and this comes out to be 0.011 s second. The earlier time was 0.028 seconds. So, for time like 0.028 seconds, the inertia of the solid cannot be neglected, and we can neglect it only after this time. In this region, up to 0.011 second, the inertia of the fluid cannot be neglected. So, over this time, we can neglect the inertia of the fluid, but cannot neglect the inertia of the solid. That is, the sphere is still accelerating during this time, but the motion of the fluid can be considered to be quasi-steady. That is, at any instant during this interval, the fluid would behave like a steady flow, except that the velocity of the fluid is changing. That seems like a contradiction, but it is not. The whole picture at time, say 0.015 seconds, whatever be the velocity of the solid sphere at that time, the fluid will behave like it is moving past the solid at that velocity, at that constant velocity. At a later time, the velocity of the solid sphere would be larger. So, the velocity field in the fluid would be like a steady velocity field with the ball motion at a larger speed. This is what is meant by quasi-steady fluid flow. A human sperm with a head of 50 micrometer diameter is traveling at 200 micrometer per second by moving its flagella in seminal plasma of kinematic viscosity about 10⁻⁴ meter square per second, which is about 100 times that of water. It develops a Reynolds number of order of 10⁻², a very small Reynolds number. Let us calculate the length over which the sperm will coast if it stops moving flagella and just coast. So that at time t is equal to 0, if it stops moving its flagella, how long would it continue moving? what distance would it cover before it comes to rest? If it is traveling at 200 micrometers per second when it stops moving its flagella. The deceleration it experiences is purely because of the viscous forces, which have been estimated earlier as mu d v naught. The mass of the sperm is like rho s d cubed, so that the deceleration is of the order of mu vs divided by rho s d square, force divided by mass. And the coasting distance can then be estimated from v naught square, the initial velocity square, divided by acceleration, a formula that you did in your high school. Or that the L by d is like rho d v naught by mu, which is like rho s by rho times Re, where Re is the Reynolds number. Since rho s by rho is like what? The density of the sperm and the density of the plasma is about the same. The Reynolds number itself becomes the non-dimensional cruising distance. The value of Reynolds number is 10 raised to minus 2. So that L by d is 10 raised to minus 2, or L is like 0.5 micrometers. This means that the sperm will stop moving almost immediately after it stops moving its flagella. We see from this that the response of fluid at low Reynolds number to the motion of the boundaries is practically instantaneous. As soon as the flagella stops moving, the response is immediate and the sperm stops moving immediately. One more example: flow through channels of slowly varying area. We have done in a fluid mechanics course the motion of a fluid in a straight pipe of a constant diameter pipe. Hagen-Poiseuille law. Now, if the pipe walls are diverging slowly, the radius is changing with x very slowly, then can we approximate this as a locally fully developed flow? If dr by dx is small, we can definitely neglect area variations and consider the channel flow to be locally fully developed. But how long should that small dr by dx be for this to be considered small so that we can make this approximation? Let's find that out. Now, from continuity equation, we get VA, velocity times the area, as constant, so that VR square, if R is the radius of the tube as a function of x, VR square is constant, so that dV by dx is obtained as minus 2V by R dr by dx. This is the change of velocity with time. The estimate of convective acceleration would be like V dV by dx. And so this would be Vc square by d into alpha. Dr by dx is replaced by alpha, the angle of the slope of the wall. This angle alpha. And the estimate of the convective force are obtained by multiplying it by the mass, which is rho L d square. And so we get the estimate of convected force as rho LD Vc square times alpha. Notice that here we consider the mass as rho times the volume, and the volume is written as d square times L. Estimate of the viscous force of mu times dl, the surface area around the walls, times the velocity gradient in the radial direction, which would be Vc by dl. This means that the inertia forces are negligible if rho L d Vc square alpha is much less than mu L Vc, or alpha is much less than mu divided by rho d Vc, which is 1 over Reynolds number. Thus, if the angle of pipe is less than 1 over Reynolds number, then the flow in the channel can be considered to be locally fully developed. This shows you the variation of alpha permissible for making this assumption versus Reynolds number. For very low Reynolds number, much larger alphas are permissible. At the critical Reynolds number 2300, it turns out to be about 0.025 degrees, or a very small angle. These examples should illustrate for you how to make approximations in various areas. We will continue with this in the next lecture. Thank you.